Alright, what's up everyone? We're going to continue. So, exposure of an aqueous solution of which ion to oxygen gas will cause color change. This is a weird wording. This is basically just asking about oxidation, right? Exposure to oxygen gas is basically oxidation. I mean, you're bound to get oxidized, right? So, basically, you're going to look at all these four and I mean, look at the oxidation states, right? Which ion needs to get oxidized more? Because when you add a compound plus O2, I mean, what happens? This compound gets oxidized most of the time, right? So we have a 2 plus chromium. This is 6 plus. Can't get oxidized more. Fe. This is 3 plus. Usually can go higher because this is the oxalate. So this is -6. So -6 plus 3. This is 3 plus as well, so 2 plus goes to maybe 3 plus, maybe 6 plus, so it's going to be A. Because this is chromium oxidation states as discussed in the previous 10 questions. Alright. 8.82 gram of Br2 is placed in an evacuated 1 liter flask and heated to 58.8 degrees Celsius. Normal boiling point of bromine. How much liquid bromine remains at equilibrium? Okay, this is just PV equals nRT. So, look out your calculator. So, normal boiling point, you're going to want to use 1 atm. Yeah, perfect. So, moles, so 8.82 over 79.90 times 2, because it's Br2, right? So that's your moles of bromine, and then you're going to multiply by 0.08206, then 58.8 plus 273, and then you're going to divide by 1. Okay. So, basically what's going on is that when you plug these all in, you get like a mixed equation. So we're going to want to figure out the moles. It's asking for moles. So the moles that works. So everything should stay constant. 1 atm, 1 liter, your temperature, everything else. So you have to figure out the moles of Br2. So you have to do it the other way. So basically, PV, so 1 times 1 over 0.08206 times 58.8 plus 273. Yeah, 0.036 moles. Multiply that by 79.90 times 2. 5.86, right? But that's your moles of gas. 5.87 moles gas. So you're going to want to subtract to find the liquid. Because this is a normal boiling point, you got the vapor pressure. You're going to have some liquid, some gas, equilibrium, right? So you figure that out, you get 2.95. Alright. 14 is very easy to screw up if you're just looking at it. You might think something else, like the dipoles cancel or stuff. No, if it was CH2F2, what I did on the local exam was I saw that and I was like, hydrogen bonding, because there's HNF. Don't make silly mistakes like that. Just draw the molecule out. It's not going to save you more than 30 seconds to just look at it and then you end up getting it wrong. So just draw it out. Okay. So CH, right? You're going to have H, 2 H's, and then H here, Cl, and Cl on top, right? Okay. Now, you know what? I'll draw this for y'all. C Cl, Cl, H. Doesn't matter where the Cl's are. But it's always better to have things symmetric, right? So you're gonna have your dipoles, negative, negative, positive, positive, right? These are gonna cancel out. So it cannot be B. What's the ion here? Can be an ion if it's in the compound. Hydrogen bonding, no. So it's LDFs. Alright. Highest melting point. Oh, I like this question. Okay. So for this, what you're gonna want to figure out is basically it's just Coulomb electrostatics. Sec. Okay. Whiteboard is tweaking. Okay. Yeah. So K20 is so you're gonna want to determine charges. Charges over size, right? -2. I'm going from A to B, so now B is +2 -2. So okay, +1 -2 and +4 -2. Okay. Okay, so it has to be D, right? No. Why? Okay. So we know A and C are wrong. So GE is larger than CA, but remember, charge trumps size. So even though GE is larger and there's going to be weaker attraction because it's K K1 K2 over R squared or R1 R2. No. It's the difference squared. I think I don't know, but that's how it works. You have your charges and then your distance for Coulomb's law. GeO2 is actually a covalent network compound, like SiO2. I see what they were doing with this problem, right? Uh, you're gonna have a lot of these. Graphene is one. Boron comes in a lot of covalent networks, right? B12. So basically, these are going to be weaker. Uh, than your ionic compounds, I believe. Wait, no. Yeah. So it's a covalent network compound, which is going to be weaker than your ionic compounds for melting point. It's basically similar to them, right? So that's why it's going to be B. Crazy, right? All right. Yeah, germanium. Okay. This is a phase diagram, right? Um, what you're going to want to do here is look at these different forms, these different allotropic forms of sulfur, and see how they vary with temperature and pressure and all that. This comes up a lot, actually. Yeah, it does. Um, there have been questions about this before. This specific phase diagram. So, A, monoclinic sulfur sublimes at 1 bar pressure. I mean, that's right here. Sublime is solid to gas. That's not what it seems like. Because these are solid, right? This is what's going on here. So that's wrong. Monoclinic sulfur is denser than ultrahydrogen sulfur. Well, look here. As temperature increases, pressure increases. When you have water's phase diagram, right? You have water is denser than ice. So ice floats in it. So the left is denser than ice when the right when the slope is negative. If it's positive, the left is less dense. So water is denser than ice. Flip it, water would be less dense than ice. Okay. So you can cross out B, right? because your water is here, your ice is here. Ice is less dense. If it was this way, this would be less dense, but it's this way. So orthorhombic is denser than monoclinic, and monoclinic sulfur is not thermodynamically stable above 119.6 degrees Celsius. It is, right? I don't see it not being. Monoclinic sulfur transforms exothermically into orthorhombic sulfur. Yeah, you're decreasing temperature, so it makes sense that you're going left, right? So you're not adding energy to go from orthorhombic to monoclinic, right? You're going the other way. You're releasing energy to go from monoclinic to orthorhombic. So yeah, be careful here, because the mistake I just made was assuming this was water, this was ice. The solid goes on the left, and the liquid goes on the right, and the gas is at the bottom. So do not make silly mistakes like that, please. Okay, now, okay. The unit cell of solid fluorite is shown below. Okay, this is a weird question, but it's not too difficult, right? Because, okay, so you have FCC, right? And you're going to have vertices and faces occupied by atoms of, well, which one is which, right? Well, your bigger atoms are going to be your anions. Smaller is your cations, right? So that's that. So calcium, you have FCC. Fluorite, but the fluorine is just occupying the cell. So fluoride is obviously not primitive cubic, definitely not. The larger open circles represent the Ca atoms. No, it's not true. Because periodically, think about it, right? Your anions are going to be larger, even though Ca is a larger atom than F, right? But still, like, periodically on the periodic table, you're going to see that anions are going to be larger because of this charge, right? F minus versus Na plus, right? Simple. F minus is larger, has less protons, right? Okay, so the larger open circle's nearest neighbors consist of 6 of the other larger open circles arranged in an octahedron. Okay, let's think about this. The fluorine neighbors have 6 of the other fluorine neighbors arranged in an octahedron. The nearest neighbors to the anions are always the cations, so this is wrong, right? The smaller closed circle's nearest neighbors consist of 8 of the larger open circles arranged in a queue. Cations, 8 of the larger. Yeah, it makes sense, because if you think about it like this, these fluorine atoms, these are called tetrahedral holes. Okay? In a face-centered cubic cell, you're going to have tetrahedral holes here. So basically what's going on, you have these 4 at the bottom, these 4 at the top. Nearest neighbors, basically they mean that these are these atoms that are more closely packed. So you're going to have these 4 at the top, and these 4 at the bottom. Not the ones on the face, no. So, yeah. Nearest neighbors, it's like, if you've heard of coordination numbers. So for hexagonal closest pact, this is 12. Cubic closest pact, I believe it's also 12. Coordination numbers. Let's see. So they're both 12. Now if you do BCC and FCC, these are 8 and 12, right? Okay. So this is FCC. So basically, you're going to have these 12 atoms all arranged in a cube. Yeah, makes sense. All right. Yeah, these questions were a little weird. Don't forget for this one that this is in picometers, and 1 picometer is 10 to the negative 10 centimeters. Yeah, weird questions. The rest is more simple, at least for me, at least. Yeah, not too bad, not too bad. All right, so we're gonna do the next two questions. All right. Okay. So these next two questions aren't too hard. It's basic calculations, right? Okay. What is Kp for the gas phase reaction of PCl5 with Cl2 at 450 Kelvin? Okay. So for this, you're gonna want to do a calculator expression, right? So follow me based on what I write on this calculator. Okay. First, what you're gonna want to do is find delta G, right? So I'm gonna write down this formula for you guys. Okay. For this, you're gonna want to go holistically, right? So you're gonna want to find the total delta H, which is going to be, look at the reaction, negative 374.9 minus negative 287.0 plus 0. Okay, negative 87.9 kilojoules per mole. So you're going to want to multiply that by 1,000. Now you have joules per mole for delta H. Now your delta S, same thing, 364.4 minus 311.8 plus 233.1. Negative 170.5 joules per mole Kelvin. So you're going to want to multiply that by 450 K, not 298 like usual. Okay, so negative 87,900. Be careful of your sign here. Minus negative 76,725. You get negative 11,175. You're going to divide that by negative 8.314. This is the thermodynamic ideal gas constant. Multiplied by 290, no, 450K again. Times, yeah, that's it, right? Now you're going to do raise it to, yeah, e to that power. You're going to get 19.8 because it's e to the power, it's the inverse of Li. All right, perfect. Now we find it at 298 Kelvin. Not too bad, right? For this, what we're going to want to do is look how we're missing out on, right? Okay, so you're going to want to do this first, minus this, times 298K. Find the total and subtract it, right? Not too bad. Okay, so yeah, so you can just use your past calculations. You get that negative 11,175 that we got before. Um, yeah. So with that information, we're going to want to do that is equal to PCl5 minus negative 267.8 kilojoules. Right? So that's going to be in joules. Right? Okay. So plus 267.8 times 1,000. So wait a second. Okay. So you're going to do delta HF minus 298. Okay, I was using 450. Yeah, be careful, be careful. Okay. Yeah, I'm still making these mistakes. It takes time to really perfect your methodology here, but okay. X minus, alright, let's call this X minus negative 267.8. So that's X plus 267.8. So you're going to subtract 267.8 times 1,000. So you're going to get B. You're going to get negative 205,000, which is basically B. Okay, it's harder to do things in your mind, so I would suggest writing them down, but I don't really have a pencil and paper to use here, so it's too complex to write out completely on text. Alright, so that's the next 10 questions. I'll see you in the next video.